So I kind of want to go back to what Eric was saying about the cloud. There was a huge cloud presence at the show at IMTS where we met. And how do you feel about that big presence of, I mean, I know that I saw some big names, Google Cloud, AWS, Microsoft. So what's your take on that when you're seeing one thing from your customers? And then I also want to ask you about AI and machine learning, and if that's anything that you're doing, and don't you need the cloud to help you with that? So help me understand that a little bit.
Yeah, I'd say, well, first of all, I'd say that pretty much all we really care about is whatever our vision is for what we want to do with the product, and that's influenced by what the customers are asking for. So we're not trendy people for the sake of being trendy. I don't think so. Other people can do cloud things if they want, but I'd say especially our user base may differ from those places. I mean, we're dealing primarily right now with aerospace and defense companies, and there's extreme aversion to the cloud. I don't have any personal aversion to the cloud. If 10 customers next week say they want a Panax instance on AWS, then that's what they're gonna get. I mean, once it works locally, it's just as easy to install it on the cloud. So if the demand arises, it's easy enough for us to address. It just hasn't so far. And then on AI and machine learning, I'm not aware of really any breakthroughs in the space that would be applicable to what we're doing. I mean, the recent breakthroughs seem to be around language models and things like this, but we're ultimately working on geometric problems, and the geometry space is infinite, so it's unclear to me how any of those types of tools would really advance what we're trying to do here.
I think it also falls into the category of the right tool for the right job. I mean, to Eric's point, could you put it on the cloud? Yes. Are there disadvantages? So there's privacy issues, but there's also typically the inputs can be fairly large. You might have a very big STL, take a while to upload that. Once we do the simulation, that can generate a lot of data. So now you have to either pick and choose what you download or download everything. That could be very, very expensive. And because the codes run so well locally, the advantage of needing 10,000 cores on an AWS server sort of drops pretty dramatically. So again, right tool for the right job.
You know, you were saying that you're part of aerospace and defense a lot in that realm. Can you give me any like case study in general terms, so that we're not giving away any information, but can you talk about anything that you've done in that realm for any particular non-named customer that you might want to tell us about?
I'll start off by saying that yeah, aerospace and defense are definitely a broad, a high percentage of our users. But the reasoning behind that is mostly because they tend to be less price sensitive and more outcome sensitive, because having parts that build successfully and don't break and things like that, and how quickly they can iterate and get to a geometry that meets their needs is really, really important. But there's no reason we couldn't. We're breaking into other markets as well. One of the markets that I didn't really see us getting into as much as the cladding market. So that's fairly common in like rocketry or jet engine type applications, where that would have been really hard / impossible for anything that wasn't really a trinket with legacy tools for a lot of the reasons that Eric mentioned before, because you have to take the directionality into account. You're not going to be scanning and rotating pattern that's going to smear all the directionality out. So I think that category of parts is a place we're very interested in doing work in. And then the other one is kind of bread and butter for these types of applications is the heat exchangers. So that kind of covers a broad variety of different companies and categories, because that can be from automotive to aerospace to defense. And those types of models are extremely, you often can't even inspect them non-destructively because they get big enough that your CTE doesn't penetrate. So yeah, a lot of our customers are actually end up using this almost as like an inspection tool to help drive those designs and get better outcomes.
Well, that makes sense. And I'm thinking too, that when we were talking about the tight tolerance compensation versus the design study, again, in a industry like aerospace and defense, where you have to have all of those parameters accounted for in order to actually know how a component will perform.
The aerospace and defense in some regards is not, that different than they have similar needs to other industries. They may have less freedom in terms of like knobs they can turn to address their issues. So I mean, aerospace is they typically want their process to be like as pre-cooked as possible. So that type of users, if we want to, let's say they're having problems with the part overheating, that type of user is probably going to be less open to optimizing like machine parameters on the fly or something like that. They're not going to like that idea because that's not pre-cooked. So they'll want or they might not want to touch the parameters at all. So for people that are open to changing the parameters but can't do it on a feedback basis, modeling is great because we can actually change those parameters on a feed forward basis. Instead of measuring something that happens during the build and modifying a parameter, we can predict it before the build and modify that parameter and then cook it down at that point. If you're averse to changing any parameters at all, we also have like a dwell time optimization for the layers. So a user might say, I don't want the bulk temperature of the part to get hotter than 200 degrees, but I'm not willing to change anything in my build except for the wait time between layers. We can tell you how long you have to wait between the layers.
So we are just about out of time. So I want to just open this up to both of you to have a last word before I ask my final question. So Eric, go ahead. I'll start with you.
I think the only thing that we haven't touched on is I think we're really just getting started. I mean, this whole concept of the multi-grid modeling that's been really a revolution in the additive modeling space for us is only 1 or 2 years old. So I think it's broadly applicable beyond just additive. I think we want to get more into optimization, but I think that there's opportunity in welding and probably other thermomechanical modeling markets beyond that. So I think we're only getting warmed up, I think, at this point.
Yeah, I mean, so a lot of the people we end up talking with have either tried process simulation in the past for additive and either made it work, or they kind of set it aside and said, this is not going to meet my needs. And they just sort of go do it the hard way with the, build, measure, fail, iterate cycle, which is very, very expensive for most of these parts, especially metals. I think for a pretty good chunk of time, there wasn't a ton of innovation in this space, but for companies that haven't looked at a simulation package in a while, I think it's worth a revisit to just see what the landscape offers. And the other kind of pushback that we sometimes get talking to new customers is we have a lot of technology that Eric talked a little bit about kind of in broad terms earlier. And one of the claims that we have is that the tool can be both faster and more accurate. And that's one of those things that as an engineer starts to set off alarm bells in your head. You're like, wait a second, it can't be both faster and more accurate unless it's just a better approach. And so part of mine and Eric's job, especially talking to new customers, is to give them enough technical detail and show them enough of how we do what we do to convince them that this is not just smoke and mirrors, that it is possible. It's just a better way to do it.
And we do give free trials, so it's not you don't have to just believe us. That's ultimately what it comes to. Try it out for a little bit and see if it does what we say it does, and make a decision based on that.
So one of the things that you just said in your last word, Eric, was looking toward the future. And that's actually my last question. So what is next for pan optimization? I know you just said you want to get into more than just additive, but do you have anything that's already in the works, or that if you could look into a crystal ball the next year or two, where do you see pan optimization being?
I guess I touched on briefly in one of my opening responses that one of the main differences in the PanX solver is that we can efficiently optimize things, but we didn't really touch too much of that in depth. So what I mean by that is that we actually, PanX, and this is unique to PanX, it computes sensitivities. So we know how sensitive every output of the model is to every input of the model, which allows us to really efficiently optimize things. So the next thing we're going to start to get into is this kind of completely unexplored adjoint sensitivity space, where we'll be able to do things like think of it as topology optimization for the build for manufacturability. So we could actually start to modify geometries or support structures to meet certain objectives you have to make sure these geometries are actually going to be buildable. And that'll be a kind of a completely different animal from anything that we discussed or have offered up until now. So I think significant resources are going to go into that over the course of the next year.
Well, great. I want to thank you both for being here, Eric Denlinger and Tyler Nelson from Pan Optimization. And thank you for joining us. Until next time, I'm Sharon Spielman with Machine Design. Stay curious.